last week we talked about data link layer, okay, and before that it was physical layer 1 and layer 2 of the OSI model, right? So this week we're going to talk about Ethernet, which is the bottom layer of the TCP/IP protocol model. Okay, we already know that the implementation of the OSI model in TCP/IP involves the combination of both layer 1 and layer 2, right? That is the physical and the data link layer, right? Okay, so this week we're going to look at the point of view of the TCP/IP protocol model, whereby we have a protocol, which is a suite of protocol for Ethernet, yeah, that's implementing these two layers, right? And Ethernet also is a very popular, very common and very popular protocol suite, yeah. And it is
present the screen.
not yet. I'm just introducing first, right? What is the topic? Give you some context, what this chapter is about, right? So this, like I said, this chapter, to give context, the previous 2 weeks that we discussed, we're looking at it from the OSI model point of view, right? So this week we're going to look at the point of view, same two layers, yeah, from the previous two weeks, but now it's more focused on the implemented protocol called Ethernet, yeah. So we've talked about Ethernet interchangeably with the OSI model because we just want to give some examples in the previous couple of weeks. But this week we're going to focus solely on the Ethernet itself, right? So there are some things that might be repeating from previous week, but we try to tie them out together by focusing on the Ethernet, right? So as usual, I'm going to present my screen and start recording. As usual, please raise hand and or unmute yourself and ask question if you need further clarification. Yeah, right. Okay. So the modules from your NetAcad will be module 7, Internet switching. Yeah? From your introduction to networks version 7, those notes available online. Yeah. Okay, for your revision, right? Further reading, go online. Yeah, with the NetAcad. Right, so chapter 5, Ethernet. In this chapter, we're going to look at 3 sections. The first one is going to focus on the Ethernet protocol itself, right? And after the explaining about Ethernet protocol, we're going to look at the switch, right? Because switches work at layer 2 and Ethernet covers layer 2 as well. Okay, Ethernet covers both layer 1 and layer 2. Okay, and then after looking at switches, right? We're going to look at ARP, okay, which stands for Address Resolution Protocol. Very important, not not very obvious because this ARP works at the background, okay, in your network stack, and it's very common actually. But since it's not initiated by users, users never knew that this ARP protocol works at the background, just like the DNS. So, but ARP is protocol at layer 2 as well. Okay, it's part of the Ethernet protocol, right? So let's start with Ethernet protocol. Okay, so we want to place the context first, yeah, to remind ourselves the Ethernet covers both from previous week or so. We already seen this. Just a recap, yeah. Ethernet covers both physical and data link layer of the OSI model. All right. And we know that data link layer is divided into two sub-layers. The upper layer that interface directly with the network layer is called the LLC, or logical link control. All right. And the second sub-layer that directly interface with the physical layer is the MAC sub-layer, which is the media access control sub-layer. And we can see that from the point of view of the Ethernet, the protocols that governs the hardware part, okay, the physical and the MAC sub-layer is F02.3, whereas the protocol that governs the LLC, or logical link control, is governed by F02.2. Okay, so I want to discuss first to make sure that we all know the terminology, yeah? Because I want to talk about what does it mean by data link layer, and then we have logical link layer, right? So we know that data link layer is layer 2 OSI model, right? And you know data, we know layer, we know what's logical and what's again layer. But why? What is this terminology? Because if you get this terminology, you'll start to see a bigger picture actually, right? When we look at networks, yeah, we know the networks form in this way. First, you have to create LAN first, right? And in a LAN, you need layer 2 device, which is a switch. This is a switch. You already know this, just a recap. So it links all the end devices together, okay? And you have a LAN. Similar, the left and the right, okay? And you may have many LANs, some bigger, some smaller, right? But the communication within the LAN, okay, are only possible between the end devices linked by that switch. Now, if you want to communicate outside of your own LAN, okay, then you have to go inter-network. Then you need a different intermediate device, which is a router. Now, we already know router is layer 3 device, which operates on the network layer. Network layer uses for the TCP/IP protocol model, IP, right? Internet protocol. Thereby, we have internet protocol address, or IP address. An IP address is required for remote communication. Okay, right. So we got that. So that means the routers connects other with another router with another router. Okay, to connect all the LANs together to form a large internetwork. Now, some terminology. Sometimes when you read the literature, when we have a connection between routers like this, we understand that is a network. So that means it is also a LAN. Okay, don't forget that. With only two host address, which is this part, this part. The interface on a router needs an address, right? So for router to router connection like this, that portion of where router and router is connected is a LAN, and only needs two address, two host address, okay, at each interface, right? So we understand that. Now, if we have a whether you have a single connection like that, or you might have many routers in between, many hops, right? So terminology, yeah. Oh, we can call this, each of these, it's on LAN, but we can also call it segment. Okay, okay. But this this because of the long history of networks, yeah, and along the way there are so many terminology. So when I said segment of a network, differentiate that from the segment in the transport layer. The segment we talk about in transport layer, we talk about the PDU name segment. But when we talk about network, as in LAN and WAN, a segment is actually a LAN. Okay, but that's not all. There's another terminology that's equivalent to segment or LAN, which is link. Okay, this is you have to read the history of the networking development since the 1960s. Then you slowly see that the terminology over some periods are used differently, and so on and so on. Nowadays, we normally say it's LAN, but some of the terminology still exists until now. So when we say data link or logical link, the keyword link here refers to LAN. Okay, so whatever you see link in data link layer or LLC, a logical link layer, we think about that link indicates is a segment or a LAN. So our conversation when we talk about this chapter, where we have a data link layer and link, you have to think of it in terms of only talking about a LAN, right? So like when you see logical link layer, that means we are talking about our conversation focus on the transport of data or frames. We talk about data link layer frames, right? Between end devices to the switch to end devices. All right. Only when we are going to the layer 3 will our frames leave our router. Because when it goes to router does not look at the frames, in the sense that in order to forward your layer 3 packets already. So router looks at layer 3, which is network layer, to look at IP address already. So to transport your data within a LAN, you only need up to layer 2. You use the address within layer 2, which is the MAC address. Okay? Right, so I just want you to realize that when you talk about link here, it's actually LAN. Okay? Right. So we go back to here. So Ethernet is a LAN technology, basically, because it's covering up to data link layer. And from the link terminology we explained early on, we know it's for us a LAN. Inside one link is one LAN, one segment of the network, right? So if you know that, then you start to realize a lot of these things, yeah. Okay, so here we are looking at the LLC sublayer. It says here places information in the frame to identify which network layer protocol is used for the frame. Coming back here, this is layer 3. So the two protocols that's being used in the TCP/IP protocol stack is this IP version 4, and together some companies haven't purchased any new equipment. Maybe still solely use IP version 4. Some companies already started to transition, because we all know that we want to end up in IP version 6, because IP version 4, the global unique IP address pool is already exhausted, and we still need more. Later, when we go to network layer, we'll see what's happening there. All right. So different protocols handle whether the communication using in terms of inter-network communication using IP version 4 or IP version 6. Okay, so data link layer LLC in literature they will call it multiplexing, demultiplexing. Okay, so it's a different kind of multiplexing, demultiplexing compared to the transport layer. Transport layer works is above network layer, right? So transport layer also work with process to process communication, right? Process to process communication over the inter-network, and how the transport layer able to work inter-network because it relies on the layer below it, network layer, to provide that inter-network routing capability, right? But at the data link layer, there's a multiplexing, demultiplexing that's happening is that data link is able to when whether it's IP version 4 or IP version 6, when it comes to data link, and when it's creating the frames don't care whether it's IP version 4 or IP version 6. To the frame, IP version 4 or IP version 6 is still the data for the frame. But when the LLC needs to pass along, okay, the data to network layer, LLC must know which protocol to pass it to. So there must be, we always seen the Ethernet field, there must be a field there to indicate what is the network layer protocol that data belongs to. And so LLC can pass it to the correct protocol handler. So if it's IP version 4 PDU, then pass it to the IP version 4 handler at the network layer. This is what we talk about here, places information in the frame to identify which network layer protocol is used for the frame. Okay? Right, so it's not mentioned here because nowadays, the way the Ethernet protocol works is, and also the network is more stable within a link. Okay, I'm going to use the terminology link, but you can understand that when I say link, it's LAN, right? Usually it's very stable, except for Wi-Fi. Okay, Wi-Fi is because we already know that it's not a very good environment, right? A lot of things can happen with Wi-Fi, but for wired Ethernet, things are very stable. Now there are two services within the LLC apart from the multiplexing, demultiplexing. Just now I mentioned is about flow control, right? Flow control, and we'll talk about flow control first. We already know that transport layer has flow control, but the flow control at the transport layer works across the inter-network. Okay, across inter-network from the source to the remote destination. That's transport layer flow control. The flow control within LLC is basically in a single link, right? In a single link. Yeah, you can see, because last time the network is not using switch. Last time we are using the bus network. You still remember bus network? The bus networks basically looks like this, right? And in this kind of network environment, there's a lot of collision happening. So when a lot of collision happening, and also sharing, and there is the network condition is not as good as the one we have right now, the modern networks. So they do have flow control. Flow control basically adjust the data flow between one node to another node, just in case the other node cannot handle the rate of the data flow. So it's basically node-to-node flow control. Okay, but nowadays it's not used in modern networks. Okay, Ethernet, this node-to-node flow control within a single link. Okay, node-to-node, not host to, not end-to-end internet network. That one is transport layer handling. Okay, basically it's not really used nowadays, right? Okay, so another thing that is not mentioned here because it's not used anymore, but if you read literature, you sometimes see, so I don't want to get confused, the error management. Remember that there is a trailer in the frame and it has a frame check sequence. And I mentioned about the frame being dropped within the link. Before we go to the router, within the link, that means the switch. Either the switch will not forward it, right? Or at the destination, the NIC will not will drop it if there was a corruption. Okay, but in this data link also there are error management. Same thing that is happening at transport layer is also provided in the data link layer, whereby if not only it will detect and drop a frame, but if you apply acknowledgement at the link layer, yeah, the concept is the same. When the destination receive the frame successfully, it will send acknowledgement. But this, remember, all this flow control, error management adds overhead, adds latency to the extra processing, right? Adds latency to the flow of your information, your data, your message through the network. So again, because of the stability and the speed and the modern network, this error management also drop and they rely instead on the transport layer error reliability. Okay, I want to provide these two information, although it's not mentioned here, because most modern network do not implement this flow control and error management at the link layer anymore. Okay, only certain legacy network still do, like NetBIOS frames. Okay, the one NetBIOS I think is one of the, I think Windows. I think NetBIOS is belong to Windows. Okay, but even NetBIOS, I'm not sure whether it's activated anymore. You can do further reading or further research on that. Okay, the NetBIOS frames protocol. All right, so the main thing right now is just this, right? Because whatever it is, whether legacy network or modern networks, we still work with two IP different IP protocols. Yeah, sorry if that's a tautology. Different internet protocol, because IP is already internet protocol again. So two different IP, so IP version 4, IP version 6. So this multiplexing, deep multiplexing at the link layer still happening, right? At the MAC sub layer, will get the information from some information from the LLC, some information the MAC itself has. For example, the hardware addressing, the MAC address can be gotten from this MAC sub layer. So MAC sub layer will actually encapsulate all this information into header frame and trailer, right? Right. So and so you can see that responsible for data encapsulation. This data encapsulation is actually the creation of the frame. Okay. And media access control means how to access the media. Okay, so it knows because it's linked, and MAC sublayer is linked to the physical layer. So MAC sublayer knows what information is required for what type of media, and that's why at the MAC sublayer is the one that is going to encapsulate different information for different media. right? The data link layer addressing is the ones that we are using MAC address. So MAC address is only for a LAN, for a link, single link. Okay, so IP address, although it's still used, yeah, at the application level. Okay, don't think that at the LAN IP address totally not used. It's there, but it's only start to be used. IP address is start to be used when it's being routed. Okay, beyond a LAN, beyond a link. Okay, within a link, IP address is still there, but it's not used. What is used is this data link layer addresses, which is the MAC address. Okay. Right? So LLC, we know, handles the communication between upper layer network layer and the lower layers, which is from the MAC sublayer. LLC also implemented in software. Okay, and implementation, because it's software, software can abstract out hardware, meaning it's independent of the hardware. Okay. Now the MAC sublayer, the second layer, so the layer below LLC and nearer to the physical layer, is the implemented in hardware. So typically, when we think about hardware, at this data link layer is the network interface card. Okay, so we have the network interface card at the end devices, and we have the network interface card at the interface of a router. But typically on a switch, we do not have to put any address at the port. Okay, right. So now we look at the second sublayer, MAC sublayer. There are two responsibilities that belong to this MAC sublayer. Yeah, data encapsulation we talked about earlier, media access control. So data encapsulation has three roles inside. Frame delimiting. Frame delimiting means basically just saying that where's the start of the frame, where's the end of the frame. Addressing, two addresses here, source address and destination address. Both of these are MAC address or hardware address. And error detection at the trailer, the FCS field, which is the frame check sequence, right? The media access control is responsible to place the frames onto the media and also to remove frames from the media. That means it's creating the frame, put it and pass it to the physical layer, but then encode it into appropriate encoding and then use whatever kind of signaling for that media. And then when the physical layer receive the bits, right, and we'll pass it up to the Mac sublayer. Mac sublayer will recognize it as a frame. Okay, will detect, oh, this is a frame. Okay, then put a logical emphasis on that frame, which is just bits from the physical layer, right? And when we talk about media recovery, we talk about the fact that for the type of contention-based access, where we have collision, how do you recover, right? So let's move on to data encapsulation. So frame delimiting, I say you basically place the starting, where's the frame starting bits, where is the end starting bits, right? Okay, addressing I already talked about is the two MAC addresses, and error detection, basically the frame check sequence. We actually use as from previous example, CRC32, right? CRC32 for as the function, as the function to create a value to represent the patterns of bits for the frame. Okay, so it's calculated before the frame is placed onto the physical media, right? And then when it reaches a switch, the switch will perform its own calculation. Okay, CRC come up with a value. The switch will compare that value with the previous value stored inside the FCS field. If they are equal, the switch will be satisfied that there is no corruption happen, right? If they are different, the switch uh, will then know that it's corrupted. Switch normally will just drop that frame, right? So to detect an error. Okay, I didn't make this. I think the previous the main lecturer last time I think did this notation and accidentally save it. Yeah. Okay. So ignore those what do you call that notation there. Right. So minimum Ethernet frame size from destination MAC address. That means here destination is here. Ignoring the preamble until FCS is 64 bytes. So minimum, if you have less than that, is considered a runt frame or a collision fragment. Okay, so even without looking at the FCS, if the switch or the NIC detect that is less than 64 bytes, okay, between destination and the end of the SCS, okay, it will just drop it. Discard means just drop it lah. Considered not a valid frame. So what happens if your data is smaller, thereby you may get smaller than 64 bytes. You pad it out. Okay, you pad it out so that it reach the minimum 64 bytes. Okay, or else that frame will be dropped.
What does
Yeah,
FCS means?
frame check sequence.
Oh, okay.
Yeah, where the CRC value is stored is a field. Okay, that's the one that we talk about. This one, error detection. Okay, the CRC function, the frame is passed through the CRC function, and the function provides you a value, a CRC value. It's stored in FCS. Okay, and then when the frame is delivered, it reach either a switch or the destination NIC. Okay, this thing will be checked again. The CRC is recalculated to come out with the CRC value. That value is then checked with the content of the CRC inside the FCS field. Okay, so that means if there's a difference in between the calculation of the previous FCS value until where it's now recalculated, there's something happened in there, right? That means corruption happened, then the frame will be dropped. So FCS is frame check sequence. FCS. All right, and the maximum is 1,518 bytes. That means you have to be very careful. I mean, the next up layer have to be very careful when it's creating the frame. Okay, so if it's too big, it's called jumbo or baby giant frames. Okay, so here it says drop the frame if it's not within the minimum and the maximum. It must be within that size. And it can vary depending on the requirement of the media. But whatever media you use, the minimum is 64, maximum is 1518. And if you think about it, this minimum and maximum at this layer, data link layer, has a impact on the size of the segment in transport layer, isn't it? Okay, and sometimes if the transport layer already set segment size as such, and then reach here and it's too big, okay, data link layer will further cut it into pieces called we call that fragments, frame fragments. Okay, no choice lah. If the PDU from up there, that means the transport layer, because for example, for the first segment, you say for the first segment, the transport layer segment the data into correct size segment. Okay, so it fits into this minimum maximum limit. But as the frame carrying that segment, it goes through different media. And if it reach a media where the media is still within 64 and that means minimum and maximum, but the size doesn't match the segment, maybe smaller, so can be further fragmented, but still within 64 and 1518 bytes, right? Just acknowledge that that can happen as we move from one segment to another segment or one link to another link. The requirement for the media changes, and the size of the segment from transport layer is now too big, even though it's within the minimum and maximum Ethernet frame size. But for that particular link, the size of the frame is too big, then it can be further fragmented, can be further. Of course, when it reach the other end of the link, right, before we move to the next link, the frames might be put back together again. All right. Right. So when you look at this Ethernet 2, that is the I think the latest version, right? Is slightly different from the previous original Ethernet version. Okay, because as we all know, protocols can be upgraded. Okay, whenever they see a need, they will upgrade the protocol. So Ethernet 2 is the Ethernet format that's used currently in the TCP/IP network, right? Okay,
What's the number for?
the 2, Ethernet 2, it's just the version. Okay, they give a different, they upgrade it. I don't know whether it's an upgrade or to satisfy certain requirements. So they make changes. Okay, but usually the changes are for the better of the protocol. So they cannot call it the original Ethernet because there are some legacy networks still use the original Ethernet, so they give it a new name lah, Ethernet 2, for example.
Only got two types. Only got is there other types of Ethernet?
No, that like the Ethernet forms the basis, and then from there they modify it for different kind of media, right? So for it's still at 02, but then they have the point 3, point 11, point whatever. So different kind of media, different technology. They will adjust the base Ethernet frame. Okay, there was a base Ethernet frame last time for the old Ethernet network, and then when the network changes already, because technology improved, then they have Ethernet 2. So Ethernet 2 becomes the base Ethernet frame. But then, of course, we know for different types of media, there are different requirements. So the header has more information, for example, or less information. So depending on the kind of technology they want to support, okay, then they give the S02.3, S02.11, something like that. For the maybe Bluetooth technology, different requirement for the info in the header. But at the very basic, all right, as the base Ethernet frame info that you must have is what you can see here: preamble, destination, source, and source address. The type is the network layer 3 type protocol type, and then the data itself. This is the PDU for the network layer, and then the frame check sequence. Okay, and then as we see at the end of last week's lecture, we can see the more complicated frame for the Wi-Fi because more information needed. So the Wi-Fi actually implements flow control and error management. Okay, but it's not at the overall LLC sublayer because overall LLC sublayer is basically governing in general, right? In general, but we only need those two flow control error management specifically for the CSMA, CA, and Wi-Fi. So CSMA, CA in Wi-Fi is activating the flow control error management for itself, implemented for itself only. Yeah. So for wired network, those things is ignored. They don't use those protocols. They don't implement those protocols. They depend on the transport layer protocol to provide flow control and error management. But for Wi-Fi, right? For Wi-Fi, wireless LAN, it is implemented as part of the CSMA-CA protocol, right? So they don't implement it in the LLC. They implement it in the IEEE.11. Okay, so you have to remember the OSI is reference. So the reference model will say that okay, here you need this. When it comes to implementation, then they can adapt it. They can refer to it, they adapt it, and they create a protocol out of it. So whether it's implemented in LLC or in their own specific protocol for specific media, then it's up to the implementer. In this case, it's IEEE. So IEEE decided that, okay, for wired LAN, there is no need for link-based flow control and error management because the network is so stable, right? So, but and you want the speed. So, but for Wi-Fi, the network is not that stable. The network is in what we call the environment. I forgot the keyword. Okay, from previous lecture, our example was a satellite communication. So wireless LAN is the same situation. So in because it's used to drop out interference and things like that. Yeah. So they implemented the flow control error management as part of the S02.11 protocols. Okay. Who knows? Maybe next time when they come up with a better technology, transmission, encoding, signaling, then it can become stable at a different frequency. Okay, then maybe flow control and error management for Wi-Fi also will be dropped. But right now it's still used now. Okay, as part of the S02.11 protocols. Right. So this description of the standard Ethernet frame. Right. Right. Frame check sequence. I already explained now. Okay, so you can see that the explanation in YouTube about CRC. That one is extra information. You will not be asked about the details of how the CRC algorithm works. But for your own, because CRC is basically used in a lot of things. Just maybe the difference would be how many bits and what kind of accuracy you want the CRC to be. So you will see that it's using polynomial algorithm, maths. So if you interested, you can follow the link in YouTube. Not sure, I didn't check this link, whether it's still there, but probably still there. Go and check the CRC. I think last week I shown you example of CLC implementation in C or C++, right? You can find very easily. Just use the keyword pseudocode CRC, or if you want to look at pseudocode, or CRC uh, implementation C or C++ or Java, right? Whichever language you want. I'm sure someone already implemented and shared, right? But at the end of the day, you don't need to know, but good for you because you want to be a software engineer, right? All these little things actually is very interesting. But it's also okay if you think about the CRC function as a black box. You feed in the pattern of bits, and it will return to you a value, and that value is the one that's stored in the frame check sequence field. All right, that value is very sensitive. The CRC is very sensitive. Okay, CRC also is used in maybe compression algorithm, things like that. There are others, yeah. There are others. Uh, 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 Maybe even better than CRC. But sometimes we also look at the computational cost. Which one is which one is simpler to execute, take less time, easier to implement in hardware, right? Sometimes the CRC is actually a fixed algorithm. So sometimes to make it fast, some manufacturer can actually perform this in hardware, in a hardware circuit, to make it even faster, right? So you don't have the translation cost between software, hardware, execution. If it's in hardware, you just run the circuit, and it's very fast. And actually, for switches and routers, if you can, you always have to balance between the speed you get by hard coding everything in hardware circuit, compared to the flexibility of software. Okay, so as a designer, you have to balance this out lah. Okay, if you put everything in hardware, then it's hard coded, no flexibility. So this is what happened actually with a lot of the consumer base. Everything is in like okay, but most enterprise level intermediate device, they normally implement like Cisco did, put in the OS, and there of course some of the more hard coded things that can be hard coded will be hard coded into circuits on the chip. But a lot of times we want to be able to have flexibility to customize our switches, customize our routers to do certain things for us. Right, so moving on to the next section, we talk more about the MAC address available in the next sublayer. Right, so MAC address is the address that's being used within a single link. Right, so let's look at the definition of this MAC address. Okay, so it's actually made up of 48-bit binary value, and the computer always works with binary digits. Okay, but as human, we are very bad with binary digits, because we just look at it as pattern. Even then, you can think about it this way: there's a reason why our phone numbers are limited to a certain number. Beyond that, it's very hard for us to remember phone number. So you try to remember, or to say or write 48 binary digits. It's very difficult, and also we are prone to making mistakes. Okay, so the easier way to express 48-bit for human consumption is convert it to hex. So in COA, you guys, I think, already do some work on this conversion between binary and hex to binary and to decimal already. Mr. Rani has already gone through with you guys.
Yeah.
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 So you know that diagram there, decimal binary hex. It represents a table whereby the numbers, the decimal number, is represented in what manner for binary and hex. We know hex is the number is 0 to 15. There's 16 digits for hex, right? And also because we don't have a number, okay, beyond 9, okay, the number 10 is actually a positional notation. So there is no number after 9 for us, decimal. So if we want, because we still want to use the very familiar digit, when it comes to hexadecimal, we have until 15, then we don't have symbols for 10, 11 for hex. So we just use alphabets, A, B, C, D, E, F, okay, to represent. So, but the thing is, it's just a symbol. If you want to do some kind of calculation with the hexadecimal number, basically you have to uh, convert it back to any other numbering, but usually it's decimal. Perform your calculation, arithmetic, and then convert back to hex, right? So, whether you expected, I think you are expected to, for IP address, you're expected to be able to know how to convert between hex, binary, decimal numbers. But in FCN, in networks course, you're not required to show conversion, how you do the conversion. In your COA, okay, I'm pretty sure Mr. Rani already told you guys, to do the conversion, you must show how to do the conversion, right? But in FCN, it's enough for you to convert, know how to convert. In the exam or test. You don't need to show the conversion method. Just use your calculator. But it's a good practice for you for COA. But we don't expect you to show conversion method. Yeah, the working for conversion. Just give us the conversion already. Enough. Okay. So hexadecimal is for us human. Easier for us. So we already know that F is 15, and 15 hex can be represented in binary by four bits. That's why we find 4 bits in binary to represent hex. Okay, if you count it, it's 1, 2, 4, 8. Add up all together, it will be 15. So F is 15. That's why hex can be represented, binary can be represented by hex. So if you have 48, you divide 48 by 4, how many hex numbers do you get? Okay, it's already given here, 12. Okay, because we have 48 bit, each hex is represented by 4 bits, so you just divide by 4, you get 12. So a complete Ethernet MAC address is represented by 12 hex digits. And you separate the hex digit. The most common way is to use colon, isn't it? Is it colon or is it dot? Right? Okay. Another thing that I think you realize is that convention. Okay, convention in the COA, maybe when you want to represent a number as hex, you either put the value. Okay, like this one, 73. I'm just gonna skip here. So if you have 73, you can either use subscript form or letter form, but sometimes it's this form. Okay, okay, because here is similar to whether you want to use this form or this form, right? Okay, to prevent confusion, or ambiguity when we look at the number. Because 73 can be base 10, could be base 16. So you have to specify, right? Cannot assume people will know straight away, right? Okay, some values and its representation in hex. Okay, so I'm not gonna show you how to convert because I know you guys learned it in COA already. Okay, you guys know already, how to convert?
Okay.
Yeah, know how to convert already?
Yeah.
Okay, yeah. For FCN, because I know you know how to convert using for COA, but FCN, because we don't really need you to show conversion work, so you can use straight away use this. Okay, so let's say 15. You can see that's F and 4 bits. Okay, because we want in FCN we want you to focus more on the networking part. All right, so every network device is connected to the same shared media, right? Especially for legacy Ethernet LAN, right? But even with the modern LAN, we're using switch. The switch still needs to know where to forward the frame. So MAC address is used for this purpose to know within the same link this frame is meant for which host, right? Which node. Okay. Mm, all MAC address must be unique to the Ethernet device or Ethernet interface. Now the thing is, MAC address you have no control over Ethernet what MAC address you will use, and neither will you care because MAC address is already predetermined, uh, hard coded or burned into your NIC hardware from the factory. So the factory, when they decide, you will see later, when they decide to use which MAC address for which NIC, they have to get this OUI. Very similar to the barcode you see on our product in the supermarket shelf. Okay, they need to get the manufacturer factory manufacturer's code, and then they will then within their own, because no manufacturer will have the same uh, code. So maybe this manufacturer and another manufacturer, they must get their own organizationally unique identifier or OUI, right? So that means we can track, actually you can track, if you look at your MAC address, you can track where or who creates your which factory it belongs to, which company produce your NIC by looking. There is such a, actually there's a website. We go to, let's see, just like MAC address lookup, whichever. Some are better than others. You just go and check. Okay, find out what's your MAC address. Later I'll show you how. Type your MAC address here, and then you will know definitely uh, who is your NIC manufacturer because of this OUI. All right. So if you're a manufacturer, you want to create a network interface card or any device with network interface card, you need to obtain this code. Okay. And then the vendor must use those code provided to them, and then they will have their own numbering. Okay, 6 hexadecimal vendor assigned value means that vendor will make sure, okay, the 6 hexadecimal vendor assigned value will be unique. Okay, and this uniqueness of the number, the MAC address is global. Is global. Whether you buy a network card in US or in Malaysia, you'll never get two network card that has similar MAC address, right? Because it is ensured to be globally unique. Because if it's not unique, let's say you went to US, then you happen to like one network card, you bought it, you bring back to Malaysia, you install into one of your host inside your LAN and duplicate, and then your network card won't work anymore because your switch will be confused. Hey, how come there's two ports having the same MAC address, right? So it has to be globally unique, right? So if you're a manufacturer, you have to follow these two simple rules provided by IEEE. All MAC address assigned to an NIC or any Ethernet device must use that vendor's assigned OUI as the first 3 bytes. 1 byte is 8 bits, so 3 times 8 is 24 bits, right? Okay, and then all MAC address with the same OUI must be assigned a unique value in the last 3 bytes. The last 3 bytes. So between the first 3 bytes and the last 3 bytes, you can have anything up to you to you as a vendor. But you just make sure the last 3 bytes, the last 24 bits must be unique, unique as well. Okay. All right. So I already mentioned that it's burn-in address. BIA means it's become part of your NICs, an identifier, right? And it says that, but you know the computer, how the computer works. In COA, I think in computer architecture, computer organization, you call it computer organization architecture, you already know about our computer system is based on the program processing, right? From the von Neumann architecture, right? Based on von Neumann architecture, any any data or instructions to be executed must be loaded into memory, isn't it? So, because all our computer right now, a majority of our computer follow von Neumann architecture. So, any data, any instructions that needs to be used by the OS or computer application, whatever, needs to be loaded into memory. So that's why when the sentence here, when the computer starts up, first thing the NIC does is copy the MAC address from the ROM. ROM stands for read-only memory. Okay, the ROM exists on the NIC itself, a network interface card, and it is there. Some of the information about the one of the information is the MAC address. So copied from ROM and placed into RAM. Okay. Now here I want it's not part of the information, but I want to let you know because some people based on legacy thinking thought that okay, maybe I don't have to use WPA for my Wi-Fi. I just make sure only my devices can connect to my Wi-Fi. How do I identify my device? MAC address. But depending on your driver, because it's in RAM already, and it is the MAC address that is in RAM that is going to be used by your network protocols, and anything in RAM can be updated while it's in RAM, isn't it? Right? So please do not depend on simply using your MAC address to protect your Wi-Fi. Meaning to say, oh, I only limit this range, this MAC address are all my devices to connect to my Wi-Fi, right? Because so I'm not sure mine are available or not, but Let me see. Go to advanced. Okay, on my Wi-Fi is not provided to me, but on yours, maybe. On your Wi-Fi, maybe, yeah. Certain Wi-Fi NIC, you can actually go to property here. Even if because this is for normal user, but if you are a programmer, you're a hacker, you can actually access where you can know where is the MAC address stored in RAM, and maybe use a software, use whatever. But usually you can check it here. Your network NIC or network adapter, you can actually change the MAC address. I'm not seeing it here, but let's say others, because depend on the drive on the driver capability. Here also, because it's VirtualBox not given to me. Let me see my Bluetooth. Does it have? Bluetooth doesn't use. Bluetooth doesn't have Mac, so definitely don't have. I don't have because maybe you guys can check on your own one. Okay, right click properties, check on the, for example, if you got your Wi-Fi, then go to properties, you go to configure here because it's part of the layer 2. Then under advanced or something like that here, see whether you can see something to do with address. Okay, if you see it, you might be able to see that you can change your MAC address, but that's not the only way to change the MAC address. What I want to say is MAC address can be spoofed. So don't depend for your Wi-Fi security to limit based on MAC address, because MAC address is stored, you can see here, stored in RAM. Whatever value stored in RAM, you can actually change, right? So you can spoof, people can spoof MAC address. So if I'm the, attacker, I can, if I know your device MAC address, I can just change my MAC address in RAM to your MAC address. And of course, not during when you're connected, because then the switch will be, the Wi-Fi access point or the switch will be confused. But when you're not connected, I connect my device, I'm using your MAC address, and if your security is based on MAC address, then I can spoof your device. Okay?
What is spoof?
Spoof means pretend to be. I pretend to be someone who I'm not. In this case, I pretend to be a device, which is I'm not. So that means because people see that MAC address is unique, right? So no one will have someone else's MAC address. They think that they can use that to provide security. That means as an authenticator lah. That means if you use it as access point, so if my access point, I go inside, I can check, right? I can say, oh, limit only devices with these MAC addresses can connect to my Wi-Fi, right? But that is dangerous. Okay, ignore that one. Go for WPA fully, because if you use that, someone else can pretend to be your device. They can just change their MAC address in memory to your MAC address, and then your access point can see already. Even your switch or whatever can see. Hey, you know what? I recognize this MAC address. They thought that means the attacker is spoofing, means pretending to be, right, another devices by using the MAC address as the authentication identifier.
Or
Okay. Yeah.
must your computer be off, and then they can
Yeah.
they can do this.
Yes. Yes. Of course, because if you connect with same MAC address at the same time, it will be highlighted lah. Then people will know. But if you know, if I know you're not online, then I connect using your MAC address. If your security is just using MAC address, then it will allow me already. That's how it knows. So don't rely on MAC address as security, because people can use MAC address to spoof. Yeah. Okay. So all right. So when a device is forwarding a message to an Ethernet network, attach header information to the frame. We know that it's done in the MAC sublayer. So the header information contains the source and destination MAC address. Okay. You can see there. If I change my MAC address in RAM, when it's time for the protocol to insert my source, the source MAC address, it will get the one from the RAM, not from the ROM, because von Neumann computer, everything must be in RAM, cannot directly use from secondary storage, and ROM is secondary storage, isn't it? So the destination and source address indicates who sends the message, right? So when you reach the destination, it will look at the source. Okay, look at the source. Okay, and it sees the MAC address. Why it needs the source? Because if it wants to reply, it will reply back to the source address. So even in LAN, we don't use this kind of way to authenticate, because it's not enough, because people can spoof the MAC address, right? Okay, so again, there are three ways you can write a MAC address. All of these three ways acceptable, but usually we go for the second one with columns. This is the most accepted convention, but all three actually all right. Okay, either you put dash to separate two hex digit, or you put colon, or you group them by 4 hex digit followed by period, four hex digit period, 4 hex digit, right? Okay, it says there depending on the OS. So different OS different lah. Okay, so Windows basically use the second one. I think Linux may use. Let me just very quickly. Okay, I don't have that. Let me just install very quickly so I can just see whether I'm curious also. Linux what? Install. Okay, let it install first. Then we check, because you can nowadays with WSL you can install Ubuntu, the bash part into Windows. So just for Windows we know. Okay, just go to command prompt, type ipconfig, and you find your main interface. In this case, my main interface, I have the Ethernet adapter, Ethernet. Okay, to look at hardware, I think you need to put all ipconfig/all. When okay, type ipconfig/all, you can see the physical address. Okay, and Windows is using dash. Well, in my computer is using dash to separate two hex digit. Right? You can try. The command is let me just clear it up. Type the ipconfig/all inside your command prompt. If you're using Linux, you basically type, oh, okay, already finished. Instead of that, I have config. Oh, IF. I want to type. Oh, actually, I want to type IF config. Yeah, IF config. It should give me the same, but just want to see how uh, how it's represented. Yeah, in Linux, you can see the format they use is colon to separate, right? Okay, you can see there. Is it the same? 98. So if I use I'm using this one is Wi-Fi. It's 98 5F. Here is 985F D3. Not sure what's the why there's a difference there. Need to find out later. Oh, here the one is got a star. This is the real one. So 9F, 5F, D3, 3E, B2, D3, all separated by dash. Here 9F, 5F is the same. Linux also detect the same Wi-Fi, but using colon in Linux, yeah? Linux bash. So this one is typically Windows. This one is Linux. Okay. So different OS uses different representation, but it's the same. The value is still the same, right? It's still that MAC address. I'm not sure about this one. You get to find out which OS use 4 hex digit followed by a period, 4 hex digit followed period, 4 hex digit, right? So this the command for Windows. You access it by type cmd and then it comes up. Okay, command prompt. You can type ipconfig /all. In Bash, if you have this installed, you type if config. Okay. If you don't have, then you have to install it as part of the NetTools utilities. Okay. Right. So MAC address are assigned to workstations, servers, printers, switches, and routers. Specifically, their network interface card, the network interface card of the workstation, servers, printers. What happens if you have two interface cards? How many MAC addresses would you have then? Two, huh? So if you have one interface card, you have one MAC address, because the MAC address is burned in onto your network interface card. So if you have more than one network interface card, then you will have more than one MAC address. One MAC address per one interface card. Okay, huh?
Sir, is it
Yeah.
possible for one device to have two NIC?
Yeah. You have, take your laptop. You have a wired NIC and wireless NIC, right?
Oh,
Yeah. So, so if you have different combination, also no problem. Normally you don't get two Wi-Fi NIC because sometimes because most people only have will be entering one Wi-Fi zone. Okay, if you have two Wi-Fi zone, uh, I'm not sure what the use case for that, but yes, for wired you can have two wired NIC, That means you want to connect to two separate LANs. Okay, so that means in order for you to be able, you might connect to two if you want to pass, you want your device to be able to forward message from one LAN to another LAN, then you might install software in your computer, maybe as a bridge acts like a switch, or as router. Okay, for Linux it's easier because Linux was designed to be it was designed earlier on to mimic Unix, which is Unix is a server operating system. So even if Linux is advertised to be desktop like Ubuntu, there you can just still install routing software. So if you're running Linux, it's easier for you to get the software because in Windows, I think routing software is a paid. I'm not sure if there's any open source or free router software in Windows, but in Linux, definitely. So your computer can be a router. Remember a router, normal router, don't talk about iOS lah, Cisco, of course, because it's got OS inside, it can go all the way up to the application, but still Cisco basically works on the basis of it will support up to layer 3. But your computer is very powerful. Your computer can have the network stack all the way up to application layer. So if you have a two network interface card and you connect to two separate network, you can install a routing software inside your computer, no problem, because routers to work minimum it need access to layer 3 network layer, but your computer can go all the way to layer 7, so definitely can do. So then your computer becomes a very powerful router, your computer. Okay, some people use their old machine rather than throw it away. They install Linux hardware requirement is very low actually. You can if you don't use it for like for desktop use, you even with 512 meg it can run, right? But limited lah. So if normal, I think within the last decade you can have like 1 gig, 2 gig very old computer. You can use your old computer headless, use it as a router. Yeah, you have one switch, two LANs. You connect into two. Maybe you buy a network adapter that plug into your computer. Then you run Linux inside there. You run routing software inside there. Your less capable computer now becomes a very powerful router. You can do that, right? One of the case lah, right? One of the use case. Some people do this. Okay. Then you can, if you want to use, it's very highly capable. You can install filter, packet filter. You can whatever lah. Now because your router is now actually a proper computer, and you can just put anything there. Firewall. You can install. A lot of Linux users do this. Yeah. So if you say, but of course it's different lah, right? Having a dedicated router and a computer is slightly different lah. Slightly different how you configure it. Okay, but it works the same. The Cisco router is basically a small form factor computer inside. Because why? Because it has an OS inside, but instead of Linux, it's running iOS. Yeah. You think about it, huh? All right. So each NIC views information to see if the destination MAC address in the frame matches the device. Well, this is what happened when at the destination computer, right? In legacy computer, in modern computers using switch, NIC still view, just in case. but definitely the switch takes over the job of making sure the frame that it forwards goes to the correct port, because the switch already see the MAC address table. That port connected to that computer, that port in my table, that computer is MAC address is this. So okay, I will switch. Okay, I will forward the frame to that. But if on legacy network, which is the bus network, where it's really a uh, shared media, that means or even if you don't have the money for a switch, you buy a hub. A hub will be layer one, so it doesn't know MAC address. It will just forward to every port. Okay, similar to the hierarchical network. If one of the hosts or node send a frame goes to every node. Every computer will receive the frame. So it's very important. In this case, the network card, when it looks at the frame, it opens up the frame header and see the destination MAC address. If the destination MAC address matches its own MAC address, then it knows that the frame is intended for itself, for this machine. If it doesn't match, what the NSC does is just to discard the frame. All right? Okay, it will discard the frame because it's not meant for it. So no point wasting CPU cycles to basically handle that frame. Okay. Okay, so now I want to talk about three types of Ethernet MAC address. The first one is the typical MAC address. This is the one that we think about. We think about MAC address to send between source to destination. This is the address that we are talking about, the Unicast MAC address. Unicast means one-to-one communication. Okay, from a single source to a single destination. Right? So Unicast MAC address mirrors the Unicast packet from the network layer. So Unicast packet, right? Unicast packet at the network layer means at the network layer, the IP address used is also the Unicast IP address. That means at the network layer, it is also a one-to-one communication. Now the thing is the MAC address have, whether you use Unicast, broadcast, or sometimes it's also leads back to the network layer. Okay, if network layer is one-to-one Unicast MAC address, then at the frame also need to have the one-to-one MAC address. Okay. Right. So when you're looking at the link, a LAN, when you're sending from the application point of view, you don't use MAC address. Think about it. There is no difference for you as the user if you want to send message inside your own LAN or to another computer remote via the internet network. For example, let's say I use a browser. Is there a difference if the browser connects to a web server inside my own LAN or a web browser that is remote? No, right? I still use the same IP address to connect. In this case, the domain name, right? But it's a translated IP address. So to connect to a web server, whether it's local or remote, I still use IP address. But we know in local, my switch doesn't use the IP address. My switch is going to use the MAC address. This is what I need you to be able to grasp. Okay, but IP address, whether local or remote, we still use. But if local, the switch does not use the IP address to deliver your frame. The switch will make use of the MAC address, your MAC address, and the local area network host connected to the switcher, the destination MAC address. Okay, but to ensure the application still work up there, there's no difference. The application doesn't think about MAC address. The application will create a socket. The socket, part of the socket is the IP address. Yeah, you guys understand, right? So when your communication become remote, to link networks together, we need routers. Routers will use the IP address because the routers will look at the destination IP address, extract the network address, and use the network address to make decision to forward to which router, next segment. But within each segment, right, the transport of the frame from one router to another router until it reach the destination network still use MAC address. Okay, so for example, let's say if I have a host connected to a switch, connected to a router, connected to a router, connected to the router, connected to the switch. This switch connected to the destination host. Okay, this is source. Maybe another destination A, destination B. Now, if it's from the source, I want to send to destination A. So although I have my own IP address, destination A also have its own IP address. I call it IP A. This one IPS. This one IPB. Of course, instead of this letter, of course, it's IP address. Yeah. So although application layer, I still need to know IPS, IPA, but the switch will use my MAC address, MAC S and MAC A. So the switch, the source will need to know the destination PC MAC address. The switch will look at the destination MAC address to know to forward to this host. Okay. Now, if I want to send from the source to a destination remote, remote destination B, the destination IP address will be needed. So the router know how to route the packets. But within the LAN, the switch will need to know the router MAC address interface here. So that means the network interface card on this router connected to the switch also have a MAC address, right? So destination MAC address will be this interface. Source will be this interface. Okay, IP still remain the same. Source IP address, destination IP address. But the source MAC address will be this for this segment. And then destination MAC address is this. Now the router forwards it to the next one. So when it travels through this, the frame travel through this segment, the source MAC address changes to be this, and destination MAC address to be this for this segment. IP source IP, destination IP don't change. Okay, next hop, you guess it, the source MAC address for this segment changes. Source MAC address this one, destination MAC address this one. Now we reach the router where the destination host is connected to the network. So in this segment now, the source MAC address will be this, and the destination MAC address will be this, and then it's delivered. So MAC address is used per segment, and it will change per segment or per link, right? But IP address is used over the entire internet network, whereas MAC address is used per link or per segment. Oh, sorry. Okay. Yeah. So go back to the three different types of MAC address. Unicast MAC address is one-to-one communication, right? To mirror the one-to-one communication on the network layer. The second type of MAC address is the broadcast. Right? The broadcast MAC address is one to all. Okay, that means from one source, it needs to be this frame needs to be delivered to all hosts within the same LAN. Okay, there's one rule. It's only within the same LAN you can do this. You cannot broadcast over the router. You cannot broadcast beyond your own LAN. Can you guess why? Think about it. What if you're allowed to broadcast over your own, beyond your own LAN?
Because IP address.
Broadcast to everybody on Earth?
Oh,
Think about it. If you
That's
can broadcast beyond your LAN, where does it end? Means it will be propagated to every computer. What's stopping it? Once the broadcast go beyond your own LAN, beyond your router, it's forwarded to another router. The router will then broadcast it. Then easily the network will just close down, will just be saturated with your broadcast. That is you broadcast. What if other people also do broadcast? Simply cannot work, right? That is why broadcast is limited within your own LAN only. Broadcast means one to all. If we take this logically, one to all in your own LAN forwarded by your router means one to all computers. So because once beyond your LAN, if your LAN is connected to the internet, means your broadcast frame will reach all over the internet, every computer on the internet. If you take it logically, because we say we define broadcast as one to all hosts. Okay, so it's not allowed to go beyond your own LAN. So it's stopped at the router. Means the router, when it looks at the destination MAC address, it will drop it. It will not forward it, even though when you look at it, it's broadcast. Can drop it. I will not forward broadcast frames. Okay. Now the broadcast frame is a special MAC address. It doesn't belong to any of the MAC address in any of the network card. Okay. Okay. It's in this form. All of the hex digit is FFFFFF. F means 15, right? 15 represented by all ones for the 4 bits. So when we have 5FFFF means all the bits for that address is ones. Okay, 11111111111 48 ones. 48 bits of 1, value of 1. Okay, that's why it's FFFFFFFF. Okay, so if you see MAC address of FFF, you know it's a broadcast MAC address. Broadcast MAC address, right? So you can see destination MAC address as OF. When a node in a network, in a LAN or in a link receive a MAC broadcast address, it will process it. Meaning to say, it will take it, the encapsulate, and pass all the way up the TCP/IP layer. Okay, it goes to network layer, it goes to transport, it goes to application. Okay. Now, I said that sometimes broadcast address must mirror what is the network layer address. Okay, meaning to say, because IP address can also do a broadcast. Again, IP layer broadcast is limited to its own LAN. So if the data link layer or the Ethernet layer sees that, hang on, the broadcast IP address, the IP address is destination is broadcast for that particular network only. So I can see, I can show you here for this network address, having a 255 as the last octet, last value is 255. 255 here means all ones, right? For IP address, immediately the frame will, destination MAC address will use also a broadcast, because switch doesn't look at this. So if you at the application level, you want to send message to every node in your LAN. Okay, so your network layer will use the IP address equivalent of a broadcast address, which is the network address followed by 255. So when you see 255 in a LAN, you know that is a broadcast. Of course, it can be, there are others, but we'll talk more about that when we do subnetting. But if you only use one network address in your LAN, then a 255 at the last octet for the IP address indicates it's a broadcast. So of course, when the frame handler, the MAC layer, sub layer, will get information from the LLC that it is a broadcast, then the destination MAC address also will be inserted with the MAC address equivalent of a broadcast address, because the switch cannot see this. It will see this one. So the broadcast MAC address will follow, okay, will follow the network destination address type. Yeah. We have the third type of MAC address. This is the multicast MAC address. Again, it follows the network layer address. Network layer address have a multicast address, then the frame will have a multicast address. What is a multicast address? So this one is in between. Remember, we have 1 to 1 and 1 to all. In between, you have 1 to many or 1 to some. Not all, but not one. Okay, sometimes, usually multicast is deployed in the sense that if only certain computer want certain messages, okay, so they subscribe. They will subscribe means they will receive. They want to receive certain information, but not all of the hosts wants to receive certain information. Okay, only some. Right? So in this case, in this manner, we want to use something called a multicast. Okay, so the group of nodes that want to receive a multicast frame must subscribe. Okay, so usually it works at the upper layer. It's a multicast IP address. So at the frame also will have a multicast destination MAC address. Okay, you cannot have a one-to-one IP address at the top, but then you send to multicast or broadcast. Doesn't match, right? It's supposed to match. Okay, if at the network layer the IP address is one to some or one to many. Okay, and so at the data link layer also the MAC address will be also one to many. Cannot have like different. Cannot have like at the IP one to many, suddenly at the data link one to one. Okay, they must be synchronized. Okay, both physical and logical address must synchronize. So if it's one to many at the network layer, then it's one to many at the data link layer. Okay, so you can see there the range provided for the IP address, the range provided for multicast for both IP version 4 and IP version 6. Okay, well, for IP and IP version 4 and IP version 6, we're going to look in more detail about their addresses later on when we go into their chapter. But for MAC address, a multicast MAC address begins with 01, 00, and 5E. Okay. All right. So just show you the range of IP version 4 is for multicast is between that range to that range. For MAC address, just starting with those 3 hexadecimal values. Okay. Right. So this come back to my explanation earlier on here. Think about my explanation in here. This explanation about the difference between the use of IP and MAC address. This slide explains that MAC address is burnt in, so the address does not change unless you spoof it. Okay, this is the limitation, because it's stored in RAM. When it's used, people can go to RAM and change the address and spoof other people's computers' MAC address. But operationally, this address does not change. Actually, it's burnt in, right? Okay. It's known as physical address because it's physically assigned to host NIC. IP address changes. Okay. If you move country, okay. I just give you that example, because there are other examples as well. But IP address allocation is actually based on region and then based on countries. So by looking at the IP address, global unique internet IP address, you can tell where that computer is located. But again, of course, hackers know how to change this, but we talk about the operational view. By looking at the IP address of the sender, the sender is actually residing in which country, because each country is allocated a range of the global unique IP address. So if you change your country, that means suddenly your IP address will change. But actually, within the country itself, if you change provider, you can, because it will change. If it's the same provider, internet service provider, if you don't pay for static IP address, every time your modem connects to the ISP, sometimes the lease expire, you're given a different IP address. So your IP address can change, unless you remain with the same ISP. You purchase every month, you pay some amount of money to your ISP, so you can book a static IP address. So as long as you're paying money to your ISP, for that IP address usage, you will have the same IP address. Okay, And most businesses actually do this, especially if they have servers, web server. Okay, they don't, because they don't want keep changing the IP address, then the domain name have to be pointing to the, they have to keep changing the domain name server to point to the IP address. If you change your IP address, your domain name now have to register to point to the new IP address, or else when the web browser resolve your domain name, it point to the older IP address, then 404 already, error. Okay. Yeah, but you need both. You need both because at the link level, MAC address is used. At the inter-network level, IP address is used. End-to-end connectivity in terms of MAC address and IP, end-to-end connectivity refers to IP address. MAC address is used within the same link. And it's only within a link. When you change link, MAC address source and destination changes based on the link. IP address, no. IP address is true end-to-end connectivity. Okay, the IP address you use for the packet will not change until it reach destination. This is what we want to see the difference between MAC address and IP address. Right, we'll talk about switches now. Okay, switches connect a host within a LAN, okay, to create the LAN itself, right? And MAC switch is a layer 2, so it's only recognize MAC address, and it's an improvement on the older technology using hubs. Okay, right? And switches have ports on them, and each port is connected directly via cable. So you're talking about wired LAN to each of the hosts. Okay. Now this MAC address table is dynamic. Okay. We don't, even if we have maybe a very good switch where we can go access inside of the switch to do configuration, we normally do not go and update the MAC address table. Okay, MAC address table is dynamic. That means the switch will learn which MAC address is mapped to which port. Port number 1, what is the MAC address of the host connected to that port. Okay, these are learned dynamically by the switch as it operates. Okay, because of convenience, and because if you have to manually update the address table, it's very troublesome. So if you switch off a switch, if it doesn't have like a ROM inside it, like Cisco, for example, even with Cisco, because we don't really want to manually update the MAC address table. Usually the MAC address table is empty when you reset your switch. And then when the switch powered on already, it will start to dynamically learn about which MAC address mapped to which port as it's forwarding frames. Okay, because the switch can open up to layer 2. It can look at the destination MAC address, source MAC address. Based on that information, it will update the MAC address table. It will learn which host with what MAC address is connected to which port. Okay, sometimes you call the MAC address as a content addressable memory, or CAM table. Content addressable memory table, or CAM table. Another name for it, yeah. Okay. All right. I said that it's the switch will build a MAC address table dynamically. That means it learns. Okay. Then it learns about the when you receive a frame, it can open, right, and so it learns from there. Oh, you know what? I received this frame from that port. What is the source MAC address for the frame coming from that port? Then I know the host that sends the frame from that port, what is that host MAC address? Isn't it? Think about it this way. The switch has empty, so it's watching all the ports, incoming frames. So if we already know that if you want to send a message to another destination inside the LAN, right, you need to provide not only IP address, even though you don't use IP address, but the MAC address, the source and destination. So when the switch receives a frame from a particular port, when it opens up the frame header and sees the source MAC address, then it knows the computer connected to that port, what is its MAC address, right? So then it will update. It says, okay, the source address is 0, let's say this is not full, this is just for example, is 00-0A. Okay, so port 1 mapped to this, already happened in 3. Okay, yeah, but of course it checks first port 1, is it I already know or not? If not, then I will add. If already got, ignore lah. I already got the info, right? Okay. If the source MAC address does exist, the switch update the refresh timer for that entry, because it also wants to forget. This part it says switch updates the refresh timer. Okay, so every elapsed time it will check. Every elapsed time it will check, just in case you unplug that computer and plug in another computer. You get what I mean? If you unplug that computer, you plug in another computer, the MAC address change. So it needs to have a timer to when to check next. Right? By default, most Ethernet switches keep an entry in the table for 5 minutes. So the process to forward the destination MAC address is, if the destination MAC address is a broadcast or multicast, the frame is flooded out all ports except the incoming port. Okay, so multicast could be is a subset of broadcast. If all the computer is a member of the multicast, then it's the same as a broadcast, isn't it? So when the switch receives a broadcast, it will flood all the other ports except the incoming port, because the incoming port is where the frame comes in from. So you don't have to broadcast to that port anymore. Okay, you broadcast to all other ports. That means you flood all other ports. All ports will be forwarded with the frame. Okay, if the destination MAC address is a unicast address, the switch will look into its MAC address table. Okay, to match the MAC address with the destination MAC address. Once you find a match, then it will choose that port. Okay, but if it's not, what does it do? If it's a unicast, but it try to match in the MAC address table, it cannot find the MAC address table because it's dynamic learning, right? It hasn't update yet. So what it does is it will perform a broadcast. Yeah, because it doesn't know. So it falls back to behaving like a hub. That's what a hub does. Every time a hub receives a frame, it will flood because it doesn't have the MAC table, it doesn't understand MAC, so it just broadcasts. A switch will perform like that if it's trying to forward the frame, but when it's searching for the destination MAC address in the MAC address table, it cannot find it. Nothing else it can do. So it floods. It sends the message to all the ports. It sends a frame to all the ports, except the incoming port, right? So there are two switching process, learning to update the dynamically update the switching table, the MAC address table, and forwarding. Forwarding means it will, if it's broadcast, it doesn't even need to check the what do you call that, the MAC address table. Okay. If it's unicast, it will check the MAC address table. If it cannot, if it can find, it knows the port, then it forward to that port. If it cannot find, then nothing else it can do. It will act as if it's broadcasting. It will flood. It will send the frame to all the ports. What will happen is the host investigate, right? Oh, destination is not my address. Destination, it will drop. Only the host with the MAC address corresponding to the destination MAC address will pick up the frame. All right. And if that host reply, then the switch can update its MAC address table. Right? Okay. So checking out the MAC address table is called filtering frames. Trying to find the MAC address, does it, the destination MAC address, does it exist in my MAC address table? And then if it does, you just check what is the port. If it doesn't, broadcast it, right? So this is called the filtering the frames. Okay. So you can, I think if you go online, you can see the video.
This video, PCA is going to send a
All right. So now it's 11:30. I want you guys to have a quick break before we finish up this lecture and proceed to our tutorial. Okay. So 15 minutes break. In the meantime, I play this video. Okay, we come back at 15 minutes from now is 11:50, is it? 11:50, yeah. Go to watch this video and then go to the toilet. Oops, sorry. Let me play it.
In this video, PCA is going to send a packet to the internet because the destination IP address is on another network. So in this case, the source MAC address is that of PCA. The destination MAC address is that of the router of 000D. So the Ethernet frame is sent to switch S1. Switch S1 receives the frame, examines the source MAC address, which is in its MAC address table. So it just simply refreshes the 5-minute timer. It examines the destination MAC address, and because that destination MAC address is not in the MAC address table of switch S1, it floods it out all ports. PCB receives the Ethernet frame, and because the destination MAC address does not match its own MAC address, it does not accept the rest of the frame. Switch S2 receives the Ethernet frame, examines the source MAC address, which is in its MAC address table, so it also simply refreshes the 5-minute timer. It examines the destination MAC address of the frame, which is not in its MAC address table, so it floods it out all ports. PCC gets the Ethernet frame, and because the destination MAC address does not match its own MAC address, it does not accept the rest of the Ethernet frame. The router receives the Ethernet frame, and because the destination MAC address does match its own MAC address, it accepts the rest of the frame. Now we'll look at the Ethernet frame coming from the router back to PCA. The source IP address is the IP address actually of a device on a remote network. The source MAC address is that of the router at 000D, and the destination MAC address is that of PCA. The frame is sent to switch S2. S2 receives it, examines the source MAC address, which is not in its MAC address table, so it adds it. It then examines the destination MAC address, which is in its MAC address table, so it forwards it out port 1. S1 receives the Ethernet frame, examines the source MAC address, which is not in its MAC address table, so it adds it to its MAC address table. It examines the destination MAC address, which is in its MAC address table, so it goes ahead and just forwards it out port 1 towards PCA. PCA examines the destination MAC address, and because it is a match, it accepts the rest of the frame.
it too. as it rings the alarm for a couple of players moving forward. Nature's playing the backside. Now a big paranoia as Nature gets the first kill onto Sinatra. So they even things up on a 4-4, but he's stuck in the back. He still manages to get a second one before he eventually gets dropped by Sick. But Gangsta's already rotated. It's a 2 versus 1. Immortals on the disadvantage as Dapper lands the last kill. And that's, Mark, 9 frenzies out of 10 in this round.
Killjoy playing towards B early on, now playing towards ropes. That's been the success story for a lot of players who play as Killjoy on the map. As I say that, though, Chemicals is taken out. Rez is going to come through very early on, mind you. That's a 3rd round Rez coming out from Sick. So illustrating orb control currently for Sentinels, who for reduced it down to 1. The only player left alive is Nature across the map. Again, we talked about Killjoy being mobile. Unfortunately, in this instance, doesn't really help them out as they did decide to go back to that B site. The defense just wasn't strong enough.
Which means now the defense numbers dwindles down on this retake, and it's just perfect positioning now. They didn't expect that Sinatra was going to be on the top of that billboard, and now shot up. The only kill that he got chimes in with the second one with the Vandal that he picked up, but that's going to end it there. Pretty decent. After they see that it's a little bit quiet, try to team up on that buddy system, and this is something that, or a concept that we talk about a lot when we're first casting this game, very similar to other tactical shooters, is the buddy system that Sentinels have. 2 players trying to work towards B main, 2 players towards mid, and then you have Dapper just lurking on the A side. Once you take control of these trades that you saw were immediate towards the mid side, and they also got a do-or-die position from Chemicals up on towards B site, then you fall back as a team, you continue as a group, and you continue to play for these trades. Sentinels are very good for this type of positioning to just allow numbers advantage when they come into sites.
Hey, I'm still going to have a ton of money. Might as well let me spend this. And again, we see this opening kill towards B. We have seen that happen almost every single round. I like the dismiss there to get away from the boom bot, so Shot Up can at least get some revenge for his teammate, as Sinatra has dialed in that early kill on B against Gangsta almost every round, it feels like.
Yeah, even how that started on how they were able to retaliate for Immortals. Sick always does that. When he puts that wall up towards that cross, he's always self-boosting at the same time, so he could maybe wide swing onto Heavens. Nice shot by Shazam to pick out Shot Up, but you saw how they tried to hold it back for Immortals. They didn't really have a fight back from B Heaven. They actually fought back from default with 2 players peeking out in that area. They make it an early advantage at the beginning, but after that, losing this player early for Shot Up towards the B Heavens, the control is back at the Sentinels, where they're looking to split into this A side, especially after that pick from Zom. They had the lockdown. That's another reason why they wants to play this passive, but unfortunately, Dapper goes for the lurk through the smoke, and that cancels out the lockdown for the attempt of a retake. Shazam on the top of the A ramp, another to fall, and just like that, in the blink of an eye, it's a 3 versus 3 with the Spike Planet at the default spot. Can this be doable for a retake? Potentially here, because you have ARs coming for the retake for Immortals, and Shot Up is already on the top of Heaven, dropping to Hell. Oh, as Zoms backs up into him, it's just going to be an easier retake. Now, as an open site, the last 2 lurking on A-ramp still. Now you force the Bladestorm out. Shazam trying to come across, and he's going to get... Oh, actually, he gets the headshot into Shot Up. Now, as they're trying to defuse, he misses the right click, and the defuse will come in favor of the Immortals to put the first point on the scoreboard. Finally, they get it done.
Timing right, and Gangsta will survive for the time being.
Still very good for Immortals. You're looking for an answer on this aggression towards the B garage. A 2 versus 2 didn't work. Passive play for retake on B didn't work. Big flank from Stani by garage. A 2. Still very good for Immortals. You're looking for an answer on this aggression towards the B garage. A 2 versus 2 didn't work. Passive play for retake on B didn't work. Big flank from Stani, by the way. But now as they push 3 players, it works out. So that's the second run in a row they do it, using 2 ultimates for 2 rounds in a row. Now they'll have a little bit less to work with as we move into the next round. But before we get into the next round, we still have a Spike Planet for Sentinels on a 1-minute advantage, where again, potential where they reset the economy, and it starts with Dapper. Headshot onto Shot Up, and Sinatra's now running in with that showstopper, looking for his opponent. Cannot, stops the lockdown, and that's a good way to pull out a utility, which means now Immortals has even less moving into the next round, with Nature now moving up on the Raptors.
Yeah, Sinatra was in a great position in Hell there, and that's exactly where he sends Nature. So it's the logic behind just putting that one out of play. There's going to be a heal that comes through. That's actually going to give away his position. There's an audible cue that comes out from that, but it doesn't scare JC Stani. At least it looked like we were seeing a heal, but he's still sitting low on 8 HP. I thought for a second we got it, but maybe not.
From Immortals stacked up in that side, giving up mid completely as Nature was trying to take an off angle. But as they lose this player, they open up the A site, and that is going to be confirmed by the Neural Theft.
Ult utilized by JC Stanny to get towards elbow. Quickly taken care of by Six. Shot Up is in position on the other side of screens, but there's a wall that's gone down from Sage, and he has no choice but to blast through it. Shazam in position, should be able to get a quick kill here on Chemicals, and does. The Odin betrays Sinatra, but it's still a player advantage for Sentinels. The 3-on-2 with the spike planted, and again, who else would you see on the flank other than Dapper? And I don't think they have any reason to believe that this is happening. There's the first kill coming out onto Gangsta. The last player remaining is Shot Up on site. Empress available, has decided not to use it. It's another round for Sentinels in the books.
Surprise, they're actually focusing back on the B side where they have more numbers eventually versus this push, especially with Sinatra with the judge. First one to fall is Gangsta, jumping around for the second kill onto Chemicals, and a big dark cover doesn't allow JC Stein to get any kills, and the B side is open just like that for Sentinels.
It feels like Sentinels have really not met much resistance, especially on that B site. The close rounds we've seen have at least seemed to be catered towards A, with some damage that was dealt early in mid. The nice paranoia coming out from Zoms and the Blade Storm. Unfortunate for Nature, who was trying his best to play defense on this A site. Shot Up, at least able to get some revenge for his fallen comrade. Drops in with Empress active, spots out that player immediately there. Shot Up still in position, but Immortals looks like they might close it out here in the first half with a round win they desperately needed. Sinatra is all the way across
Legend of Total War here with a new campaign series for Medieval 2 Total War. So I've been this, but it turned out, and I'm glad people commented straight away because it gave me the opportunity to just take it straight back down, that even though I went down here to select very hard difficulty, I must have done that, and it wasn't on the hardest difficulty. So a little bit of an oversight by me, but I had only recorded 2 episodes. I can easily just redo it. I don't play on normal difficulty. It'd be embarrassing for me to do that. And I'm glad that people commented straight away. So thanks to you those recorded difficulty. That even though I went down here to select very hard difficulty, I must have done that. And down here to select very hard difficulty, I must have done that. And it wasn't on the hardest difficulty. So a little bit of an oversight by me, but I had.
The most serene Republic of Venice, as it is known, has become a power through control of trade. War is simply another avenue for commerce.
Something on normal difficulty, I made a mistake. Got to take it down. Easily just redo it. Alright, so first thing we're going to do is take Zagreb, and of course, the way I play Medieval 2 is completely different from the newer Total Wars. Those of you who have been introduced to me via Warhammer, it's going to be a very different experience when playing Medieval 2. If you're not familiar with Medieval 2, my recommendation is, if you play Warhammer when you're a little bit bored of that, get Medieval 2. It is, in my opinion, the best Total War. It's not the hardest Total War. In fact, it's probably the easiest Total War. But it is the most immersive, it's the most fun, and there's so many goddamn awesome mods. And to be honest, it's actually got a better Warhammer mod than Total War Warhammer. Like, there's Call of Warhammer, and I think the beginning of the End Time one just looks amazing.
Welcome back.
Oh,
Alright, so now we are looking at switching speeds and forwarding methods. Yeah. Alright, so these are forwarding methods on Cisco switches, depending on the model and depending on the usage from the point of view of the network administrator, which one they want to purchase. So we have store and forward and cut through. Okay, these are the switching methods. Now sometimes the Cisco switch you can is good enough that you can select which one you want, either store and forward or cut through. So for this kind of models, you can actually configure the switch, right? Whether it wants to do store and forward or cut through. But usually different model, different way to do the forwarding. So what's the difference between these two? One of them, we look at the store and forward first. The switch will receive the entire frame, means it gets the entire frame, that means from the start to the end frame, calculates the CRC. This is typically how we imagine a switch will work, right, with a frame. And then if the CRC is valid, then the switch will perform the lookup from the MAC address table to look at the destination address and check the outgoing interface and then forward it to the port. This is how we imagine it's going to happen, right? And then cut through is an attempt to be faster, right? So this only works on a very stable network because you just want to open up the header, check the destination address, and then straight away forward the frame without checking for the CRC. You assume that there's no need to check the CRC, that the frame definitely going to be okay, and you forward it directly. Okay. So for cut through, just get enough of the frame to get the header part. Check inside the header for the destination field for the MAC address destination address, and then when you get the destination address, check your table, and then without processing the entire frame, forward the frame straight to that port. Right. So the first one, make sure the frame is not corrupted before forwarding. Okay. So the second one, value speed rather than checking for corruption. Okay. And for most LAN with a wired network, with a very stable network, cut through maybe is suitable, right? You can see a cut through switching. So just enough of the frame to read the destination MAC address. So you can check in your MAC address table. So no error checking done. Okay. So there are two types of cut through switching. Fast forward switching offers the lowest level latency. Latency means delay. Remember, we talked about bandwidth and throughput, and how throughput is affected by the latency inside the network. And one of the source of latency we talk about is the intermediate device, for example, switch. The switching takes time. The check the loading of the frame, interpreting the frame, checking, all this is latency. Delay, it introduces delay into the forwarding of the message frame, right? So the most common cut-through switching is a fast-forward switching. This is the fastest one. Lowest level latency means the fastest method. The switch immediately forwards a packet after reading destination address. Of course, checking through the MAC address table to determine the port. Fragment-free switching is when it stores the first 64 bytes of the frame before forwarding, right? So at least it knows that, because remember 64 bytes is, what is a 64 bytes? Is the minimum, right? Minimum size. So if the size of the frame is less than 64, you know it's a run. No need to forward lah, right? So because maybe CRC checking is fine, but what about fragment? So this one is compromising lah. At least I will check. I will not check CRC, but at least I will check for run fragment. Okay, try to store the first 64 bytes before forwarding. That means you can check whether the frame is actually less than 64 or 64 and above. Okay, 64 and above, forward. Run frame, drop it. So it's a compromise between store and forward and fast forward switching. Okay, the most secure one is of course is store and forward, but it's the most slowest because you need to check. You need to grab the entire frame in order to do the CRC, isn't it? Okay, so if you want faster speed, faster switching, you go for cut through. The fastest one will be fast forward. Just read as until you get the destination MAC address. Check the port, then forward it. No need to read the rest of the frame. Just grab the entire frame, forward it through. Fragment free, well, compromise. I will not check for CRC, but I'll check for frame, right? Okay, now memory buffering. There are two types of memory buffering. What do you mean by memory buffering? Because if if the switch gets the frame, it needs somewhere to place it, right? Okay, so the somewhere we need to place the frame is the buffer, right? So buffering can be used also if destination port is busy due to congestion. So basically, okay, I know it's busy, so I'm just gonna hold it for a while, in the hope that if I delay forwarding the frame, the uh, the destination will be able to cope, right? So there are two types of memory buffering. Port-based memory means frames are stored in the buffer that's linked to specific ports, whether it's incoming or outgoing. Okay, of course, ports will, if we talk about outgoing, if if frames are delayed, then it will be queued up in the buffer for the output port. If it's incoming, there will be those incoming frames will be buffered at the incoming port. So that means just allocating different memory buffer area for different ports for different purpose. Okay, so those are port-based memory. This is useful when you know you only want to buffer due to delay, and delay usually is can be identified per host. So this one is per host. Okay, other hosts maybe no need to delay. Some hosts need to delay, for example. So then in that case, you may want to use port-based memory. The second one is shared memory, whereby the memory you just have a buffer. So it doesn't matter which port. Okay, if you want to do you want to buffer the frames, put them into the shared memory. Okay, all ports will use the same shared memory buffer. Okay, so these two different methods. Next, we talk about duplex setting. I think we talked about this earlier, so we're going to go through very quickly. Half duplex mean only one type of communication at any one time. So if you're receiving, you can only do receiving. If you're sending, you can only do sending. You cannot have both receiving and sending at the same time. It takes turn, basically. Receive, send, receive. Okay. Now, if anyone violates this, there will be collision. Okay, this is what you see in a network based on hub. Okay, right? In order to alleviate this, of course, they develop switch. Okay, they develop switch. Switch allow us to have full duplex because switch is physical switch. So once you switch two hosts to talk together, it becomes point to point. Physically, like point to point, isn't it? Because you connect those two hosts physically, yeah. Okay, in the switch, right? Then full duplex means send and receive at the same time is achieved by having the standard using the UTP cables, STP cables, whereby you have different wires or different but there's one pair of wire for sending, one pair of wire for receiving, for example. That means they are separate channels, so can do full duplex communication. Okay, but need both party and the communication to be supporting full duplex. If one party only do half duplex, The other one, even though capable of full duplex, will fall down to half duplex as well. Because you're actually switching, there's no collision. It becomes point to point. There's no collision because the communication is not shared. Okay. In this case, collision detect, because Ethernet, remember, CSMA used to be CSMA/CD, so the CD part is disabled. Okay, there is no longer need to detect collision because there's no collision happening because it's a switch port physically connecting two ports together. When it's physically connected, other hosts cannot join into the conversation, so thereby it's collision free. Okay. So most devices use auto negation, which enables two devices to automatically exchange information about speed and duplex capability and choose highest performance mode. Auto negotiation means they interrogate each other. I am full duplex, so I can send full duplex. Oh, I'm half duplex. So once they negotiate like this, if the device have auto negotiation, means they can actually set their performance based on the lowest. In network, you can see that the performance of the network is based on the lowest capability of whichever component of your network. For example, if you switch one, very good, can support full duplex, but if you switch to half duplex, then switch one will fall down to half duplex to support S2. Right? So we call this, when you have a mixture of full and half duplex, then whereby the performance go down to half duplex, we call that a duplex mismatch. And this is common cause of performance issue. Right? Okay. So nowadays it's less likely to happen because by default most switches, most network card supports full duplex. Okay, but during the transition between half to full duplex last time, this is a big problem lah. Especially companies that there's a lot of networking devices and end devices, so they have to upgrade slowly. So they still have some half duplex for the all devices, full duplex for the new devices. So sometimes you get this duplex mismatch. Okay, but once you transition to everything is the latest, I will imagine that you don't have any problem anymore. You will have full duplex capability for all your devices. Then your network will be running at their maximum capacity, capability, right? Okay. Auto MDIX is talking about the crossover and straight-through cable interface or port that has this auto MDIX feature. Means you don't really look at whether you're supposed to use straight through or crossover cable anymore, because the ports they will switch. Okay, they will switch themselves. If you need crossover cable, then instead of you having to physically go and get a cable that is crossover cable, the port itself will switch so that even if you're using straight through cable, the communication works. All right. Okay, so for Cisco switches that supports the iOS 12.2 80AC and above, starting from there, all the switches are capable of auto MDIX. Older ones, no. Older ones, then no auto MDX. Means if you connect those two switches together, you need to get a crossover cable. But for the version shown and above, all the ports on the switch have this auto MDIX. So that means save you the hassle and also the cost of getting crossover cable, so you can use straight through, even though switch to switch. Okay. Right, the final one want to talk about ARP, Address Resolution Protocol. I just want to let you know that Address Resolution Protocol, it means this. You have the IP address of your destination in your LAN, and you send a message, but then your data link layer do not have the MAC address of that destination PC. What can you do? How does your data link layer know about any other PC on the LAN MAC address? Remember, from the user point of view, the user need to know the IP address of the computer. The application will request, oh, okay, what's the IP address? But that's all the user see. User don't care about MAC address, don't even know about MAC address, yeah? But at the data link layer, the encapsulation process needs to have the destination MAC address. What if and how did your computer knows what is the destination MAC address? Where can you get it from? This is the thing. The IP, okay, no problem, because you use IP, you're familiar with IP, you simply get the IP address from the other person. But for MAC address, not many people know MAC address, and also there is this protocol called ARP that does the thing for us automatically, right? Okay, so here this slide say on the same network, MAC address is used. Okay, but IP address is not only used in the inter-network. Within the same network also, IP address is used in the sense that from application point of view. Application point of view, transport layer point of view, IP address is needed. Okay, so but MAC address is also really the one that switch will operate on, not IP address. So even though you know IP address to send to the local host, you still need MAC address. But the question is, how do you know? How do you get? If you don't know what's the MAC address, how do you know that? Right? Okay, so let's check. So here, destination is on a remote network. When the destination IP address is on a remote network, the destination MAC address will be the address of the host default. So basically, our MAC address is in the same link. We'll talk about it. This one and this one IP address remain the same over internet network, but MAC address will be here. And then the next segment, MAC address will be here. Then finally, the MAC address will be here. Always change, right? MAC address always change when you go from one segment to one segment. But IP address remain the same over the whole journey. Okay, this one we talk about earlier on, right? You can see here the changes: source, destination. If the message frame is moving this way, source, destination, source, destination. So we're talking about MAC address, but IP address no change. Okay, this is the point. This is a point that this diagram is why it's showing you MAC address, MAC address, MAC address. Okay. So coming back to ARP, ARP is a protocol, okay, used by IP version 4, okay, to resolve IP version 4 into MAC address. Let's say you have the IP address. You want to send your message to that computer. Let's say in the same LAN. Like you don't have the MAC address, destination MAC address. How are you going to achieve that? Because frame needs the destination MAC address so the switch can perform its job. The only way to get that destination MAC address, if your computer don't have it, is to use this ARP. That's why its name is Address Resolution Protocol, to resolve the destination MAC address from its destination IP address. Okay. So for IP version 6 is different. IP version 6 don't use ARP. It's use the updated ICMP version 6 protocol, which do the same thing, but is now part of the ICMP version 6 protocol. So the ARP is dropped in IP version 6. Okay, and it's combined with the ICMP version 6 protocol for IP version 6. IP version 4 use ARP. Okay, so let's look at ARP. Right, so the scenario is this. If a device wants to send an Ethernet frame, the frame header must have these two, destination and source MAC address. Okay. Now, the thing is, when that sending device do not have this, it has the destination IP address, but it doesn't have destination MAC address. So how? So that's the purpose for ARP. Because the node needs to find a way to find the MAC address of the destination. Okay, inside the LAN. Yeah, Ethernet link is one LAN, huh? So to resolve the MAC address, the device use the ARP. Okay, so ARP has two basic functionality. One is this one, resolving IP version 4 address to MAC address. I have the IP address, destination IP address. I don't have the destination MAC address. How do I do that? So I use ARP. Okay, so do I have to do this every time? Once I know destination MAC address, do I need to do it again later? No, because you will then store it, you update your ARP table. So this ARP table is available or maintained in each computer. Each computer in the LAN dynamically build the ARP table. So you only actually need to do it once. Okay. Okay. So once it gets once it runs ARP, gets the destination MAC address, it will update the ARP table. Okay. So basically, before it's used ARP, it checks the ARP table first. If I have this IP address, destination IP address, what is its MAC address? If there's no entry, then use ARP. If there's entry, take that value and use it in the frame. Okay. You can see ARP table. Okay. It's maintained inside your computer by the OS. Yeah. Okay, so I'm gonna type the ARP. I think it's print. Oh, A. So just type ARP A. You can see your own ARP table. So you can see the IP address that my computer knows belong in this network is, there's a mapping between that and its physical address, the MAC address. Okay, static means this was determined by the what do you call that the DHCP. Dynamic means it creates it use ARP. Dynamic is the one that's using ARP to update the table. Okay, so command you can use is ARP-A, ARP-A. Okay, all right. So what will happen is if my device has the IP address of destination device, okay, then I don't have its MAC address, then I check my ARP table in my own computer. Is there. Check the ARP table, locate the IP address. Okay, if it exists, then look at the corresponding MAC address. then I get the MAC address, and that is the destination MAC address. But if it does not exist, I check the IP address, I don't have the entry, means that means I don't have the MAC address. So I need to do the ARP request. Okay. Now, if the IP address is not on your own network, it's a different network, means it's outside your LAN. Okay, the ARP table will look for the gateways MAC address, because if the IP address did not belong to your own network, means you're sending a request to, you're sending a message to outside your LAN. Sending outside the LAN, you have to go via the gateway. So instead, you check the ARP table for the IP address of the default gateway and find its corresponding MAC address. Okay. Right. So let's say you try to find inside and you cannot find the IP address entry in your ARP table. So you need to do the ARP request. ARP request is by default a broadcast frame. Because you see, you don't know, right? Your destination becomes broadcast, and your message is an ARP request. Okay, all the other computers will understand this ARP request. Only the host with the same IP address as the destination IP address will reply the ARP request. Okay, so ARP message are encapsulated directly within an Ethernet frame. It's inside the Ethernet frame. There is no ARP information within the network layer. Network layer is network layer. So where is this ARP message going to be embedded in? Inside Ethernet frame. Okay, so ARP request message includes the ARP message inside the Ethernet frame. It includes the IP version 4 address and the target MAC address. Okay. Right. So it's broadcast because your computer doesn't know which computer what is their MAC address. Your computer only knows IP address only. So the ARP is a broadcast. It goes to all the computer in the network, right? And then when each of the PC receive the ARP request, they will check is it intended for them by looking at the IP destination IP address. If it's not intended for them, then they will just ignore the ARP frame. Okay. If it is intended for that particular PC, the PC will reply. Okay, will reply. Okay, will reply, and then when it replies, the reply message contains the requested MAC address, and then the original sender will update its ARP table to store it for future, and then able to complete the frame. Okay, now it has the destination MAC address. You insert it in the frame and then send the frame to the destination. All right. Okay, so only the device with IP version 4 address associated will reply. ARP require. The reply will have the sender's IP version 4 address and sender's MAC address. All right. So entries in the ARP table, because it's dynamically updated, are timestamped. Right. So sometimes devices change their IP address. So when devices change their IP address, MAC address they cannot change, right? Unless they want to spoof. But devices usually they don't change MAC address; they change IP address. So if they change IP address, as is usual for Wi-Fi, right? Then the information inside the ARP table becomes stale. Okay, so if the sender still rely on the ARP table and send a frame, if we do not receive a frame and a reply, okay, then the entry is removed from ARP table. So time to time, the ARP table, the ARP process will update, refresh its ARP table, just in case some of the information inside the ARP table becomes stale. That means it's already changed, but you haven't updated. So to keep it recent, yeah. Okay. So what's inside the ARP table again? A mapping between IP address and MAC address. Okay. Please view the video on your own time. Okay. This video basically shows you the ARP operation, the ARP request and reply. Yeah, that's what I've explained. Okay. Right. So ARP role in remote communication. Now ARP, because it's broadcast, it actually should be limited inside the local network, right? But in terms of you try to send a message to a remote host. You're sending a message to a remote host. So you don't, when you notice that it's remote host network address is not the same as your own network address. Okay, so basically your ARP table, of course, will not store those kind of information because it's remote. So what will happen is if you are sending to a remote host, okay, of course the remote host you don't have the MAC address, but to send to remote host means you have to send to the default gateway. And then the default gateway is a router that will forward your packet, right? So basically, if it's a remote host IP address, the MAC address will be changed to the default gateway. And if you don't have the MAC address of the default gateway, you will obviously you will send the ARP request. Okay, and once you have that, you will update. Okay, so you can see in the event that the gateway entry is not in the table, an ARP request is used to retrieve the MAC address associated with the IP address of the router interface. Okay. If that means the IP MAC address partnership inside your ARP table of the router gateway. Okay, you want to update. If you don't have the MAC address of your default gateway, then you use ARP, and then the default gateway interface will reply, ARP reply, you get the MAC address, then you can then use it if you want to send messages to any host which is remote. Any host that is remote will automatically get the MAC address of your default gateway. Right? Understood? Okay. So when a host when a host creates a packet for destination, it compares the destination IP address with its own IP address, assuming that the two IP addresses are located on the same layer 3 network. This is whether it's remote or local. If destination IP version 4 host is on the local, then we'll use the MAC address of the device as destination MAC address. If the destination is not local, because look at the network address is not same address as your network address, so this is remote, right? The source will use ARP process to get the MAC address of the default gateway MAC address. If the gateway entry is not in the table, then retrieve the MAC address for the IP address of the router interface. Okay, that means a remote IP address will be paired with the default gateway MAC address. Okay, if you don't have the remote, the default gateway MAC address, you use the ARP request to get it. Once you get it, then IP address still remote IP address, but for the purpose of frame forwarding in the link, you put destination MAC address as the MAC address of the router default gateway interface, right? Okay. So again, please watch the video on your own. Okay. Right, so entries from the ARP table are not permanent, as I explained before. If you use DHCP, IP address can change, or sometimes people unplug and plug in, or they manually change the IP address. So cannot be more permanent, right? IP address, only the MAC address should be permanent. So IP address being impermanent means ARP needs a way to forget entries. Forget entry means removing it from the ARP table. So ARP uses a timer. Once the timer elapses, okay, and then entries will be removed. Of course, if entries removed, the ARP process will follow in the because there's no entry anymore. In this way, ARP table does not become out of date due to many things lah, many ways people can change IP address, right? So we don't want the IP address mapping with MAC address to be permanent because IP address can change. So this is the way lah, using a timer. Okay, the timer elapses, remove entry, and this can be targeted per entry. Once you enter an entry into the ARP table, then you start the timer for that. Okay. Okay, it's more granular lah, better than just one timer for the whole table. Can also, but which one more efficient? I think about per entry. It depends on how the OS implements it, right? So if you just want to show IP ARP, right? It will display the table on the Cisco router. Cisco router contains the ARP table. Switch don't have, okay. On your own computer, as shown you earlier, is ARP-A. And you'll see it. Okay, you'll see it. And you can have other options, ARP-A like that, other options, ARP. Let me see, you can see -A is display, and then G is the same, V, current entry, in verbose mode, more information. If you just want to find for a particular internet address, you can specify that. So these are the options that you can control when you interrogate the ARP table, right? Okay, so there are some issues. ARP request is broadcast. Since you don't know the MAC address, so you broadcast, right? Now, if it has to strike a perfect balance, because too many ARP broadcasts means your local area network will be flooded with broadcasts most of the time, right? Okay, so and you can see this typically when many devices is switched on at the same time. You'll see the delay at the beginning of that time where the ARP table is populated, right? Another problem with ARP is a security risk. Okay, a threat actor here means a hacker or a bad person like want to hack or whatever. Okay, they can use something called ARP spoofing. Again, you will see a lot of spoofing this keyword. Okay, just to remind you, just now someone asked what spoofing. Spoofing means to pretend. Okay, to pretend to be something or someone that you're actually not. Okay, so that people are full or devices are full, and then they give you same access or same privilege to the person or device that you're spoofing. Right? So in ARP, the security risk is ARP spoofing, and this is called ARP poisoning attack. Okay, so the threat actor will, instead of the real device, because you see the sender wants to know the MAC address of the destination PC. What happens is that the threat actor pretends to be the destination PC. So instead of the correct destination PC replying the ARP request, the fake destination PC, which is the threat actor is there, is the one that reply, and it replies with its own MAC address. So the sender doesn't know. The sender receive it, think, oh, okay, I got it already. I got the destination MAC address. So now every message, okay, that is sent by the sender will be received by the threat actor instead. Okay, you guys get this? You're pretending your machine pretending to be the other machine. So now after the ARP reply, the sender will keep sending message to you, thinking that you are the correct PC.
So
Okay,
hacking like that. So,
yeah, sorry.
so use this for hacking also.
Yeah. See, if you that means now you get message from then you can pretend lah. You can pretend. So depending on the conversation, you might be able to read, you might be able to view, to get whatever information you need from that particular computer. Okay, and then if you, because you now assume the role of the original computer, you get the same privilege. And if the computer you take over, you pretend to be have a very high clearance level, then you automatically get the high what lah? That means you can ask, you can whatever through the network communication. The other machine have no idea. Okay, have no idea. So all the network messages is coming to you. You can view whatever, isn't it? So this is a big threat lah. Last time when this ARP was created, the network environment is very trustworthy. Okay, at the early stage, it's because it's used in university, it's used in government office traditionally. Okay, but now in the modern era, this is different already. We are living in different situation where we have all these threat actors already. These hackers, these criminals, all this, they want to hack for whatever purpose, lah, right? So we find that the ARP has a limitation, lah. Okay, in terms of security. Okay, that's why for IP version 6, I think they fixed this already. Okay, moving forward to the new protocol, they fix some of the issues lah. Right? So enterprise level switches include mitigation technique. Mitigation means prevention. They call it dynamic ARP inspection, DAI. Okay, right. So I said beyond the scope of this course, it's possible that you will maybe learn about this in future courses lah. Okay, so but normal switch, I don't think it has any mitigation technique lah. Of course, when you are on the enterprise level, you want to be, the security is become very important. So you buy more expensive switches. More expensive switches has a way to deal with poisoning attack, ARP poisoning attack. Okay. So basically, dynamic ARP inspection, I think, is find a way to identify rogue ARP replier. Okay, so this is a example that I gave earlier on. Right? They pretend the device by the threat actor, they pretend to be the actual device without the knowledge of the sender. And then after successfully doing ARP spoofing, the threat actor device can now receive all communication from the sender, meant for the original computer, right? Right. So IP version 6 neighbor discovery. This is IP version 6 address resolution using ICMP version 6. Neighbor solicitation and neighbor advertisement messages. These are two updated feature inside IP version 6. Okay, please have a look at it. But the thing is, I think when we are touching on IP version 6 in the network layer later, we're gonna go back to this again. We're gonna look at this again, the neighbor discovery messages and router advertisement messages. Okay, so have a look at this. Okay, but we're gonna cover this again in the coming chapters, right? Okay, sorry about this. Means I've run out of time for the tutorial actually, but don't worry, we're gonna spend enough time to do this tutorial. But I do want to focus on the lecture because we want to, if we look at the future one, I want to spend more time later on the IP addressing, IP addressing, subnetting, and VSM, because this form part of your very important part of SBA is about 40%. So I want to focus on the lecture. The tutorial, of course, is important, but we can go on it a bit slowly compared to the to reach the network layer. I think after this is network layer, right? So, but this can I confirm with you guys this Saturday, right? Maybe we can allocate some time for the tutorial. But this Saturday, is it afternoon or morning? Because I have another class also FCN. Do you guys remember? Do we set morning or afternoon? Replacement. Just remember or not?
Not sure.
Not sure. Okay. What about Noel?
Morning, if not mistaken.
Morning lah kan? I will confirm lah. Right, but I will update our event calendar lah, to reflect that. Okay, I will check with the other class. Okay, then I'll update the calendar. I think you guys will be informed via the calendar, right? It will show up there. All right. Okay, so I will see you again on Friday. We have the practical session, right? Oh no, when is the practical session? Practical session, yeah, morning on Friday. So maybe I'll spend half an hour of the practical on the tutorial. Any problem with the tutorial question so far?
So far, no.
So far, okay.
Yeah. All right. So about today's lecture, any doubt, any questions?
No.
Not so far. Okay. All right. So I think that's it for now. Let me just start presenting this. All right. I will see you guys in the next class. Yeah.
Okay, sir.
Thank you very much.
Okay, sir. Thank you.